All right, so welcome back. Now let's take a look at R4. This section is about integer and rational exponents. Okay, so we're going to first of all talk about and explore each of the rules for exponents individually. So the first one that we're going to talk about is called the product rule for exponents. If we have a situation here like a to the m power times a to the n power, this product rule says, well, we can just think of this as a raised to the m plus n. Okay, so the important stipulation or requirement here is that the base is the same. So a is the same in both cases. Okay, and then these numbers don't have to be the same. But as long as that holds, we can go ahead and combine it like this. So let's see what that looks like. Let's say we had 2 raised to the 5th power times 2 raised to the 3rd power. So the bases are the same. So 2 is the same in both cases. The exponents can be different. So why does this rule work? Well, we already know that 2 raised to the 5th power is just 2 multiplied by itself 5 times. 2 raised to the 3rd power is 2 multiplied by itself 3 times. Well, then how many 2's are we left with? We're going to be ending up multiplying 8 of these 2's together, which we can just kind of shorten as 2 raised to the 8th power, right? So that's just 5 plus 3, or 8. Okay? So let's look at a couple of these examples here. To start off, we've got y to the 4th power times y to the 7th power. Let's go ahead and just add those exponents according to the rule, right? The base is the same, it's y. So that's not a problem. So we're left with y to the 11th, y to the 4 plus 7, which is y to the 11th power. Now we've got, in part b, we've got b squared times b to the 9th times b. Now when you have a b by itself like that, it's got an exponent, it's just an invisible exponent. It's just a 1 here, right? It's just 1b by itself being multiplied with the rest of these. So that's just a 1. Now let's go ahead and use our product rule. It says, well, we can just add those exponents up. 2 plus 9 plus 1. And that's because the base, which is the letter b, is the same. And that's going to come out to b raised to the 12th power. Okay. Now here in part C, we've got variables raised to powers, but we've also got some numbers here. These numbers are called coefficients. They're being multiplied with these variables. So it might be helpful to kind of switch the order around in here, and we can do that with numbers and values that are just being multiplied. It doesn't matter which order we put them in. So let's have these numbers out front here. 6 times 9 times 2. And if you like, you can consider them in parentheses. Doesn't really matter. If it helps you just kind of group it visually. And then let's consider all the z's by themselves in another group of parentheses. Z to the 5th, z to the 3rd, and remember that z, you don't see an exponent there, that means there's an invisible 1. Z to the 1st power. Okay? So what we can do here is we can multiply together these values. So this is 54 times 2, that's going to come out to 108. And then we're going to add up the exponents here for these z's. So we've got 5 plus 3 plus 1. This is going to come out to 108 times z to the 9th power. All right. So far, so good, hopefully. D is pretty much the same thing as part C. We've just got a couple of negatives here to deal with. So let's bring those out front. Let's group them together. -4 times 3 times -2. And then let's put those m's together. So again, they're all the same letter, same base. This is going to allow us to use the product rule. If, for example, we had an n in here or a z or something like that, that number would not combine with the rest of these. That's just something we'd have to write by itself on the side and just leave it. Just kind of put it in as an endpoint. All right, so -4 times 3 times -2. This is going to come out to positive 24. We've got m raised to the 5th power, so we're going to add it 5 plus 5 plus 9. And this is going to come out to 24 times m raised to the 19th power. All right. So that is our product rule. It's our first rule for exponents. The next thing we're going to look at is called a power rule. Okay, so this is when we have a term that already has an exponent, and then we're raising it to another power. Okay, so this is kind of an exponent raised to an exponent situation here. So you've got 3 different ways this might look. We've got a to the m, in parentheses here, further raised to the n power. And what we do with this kind of case is we go ahead and we multiply these exponents. So this becomes a to the m times n. Now say you have, in parentheses, a times b, all of it raised to the m power. So now this a is being raised to the m power, but so is this b. So this is going to be written as a to the m times b to the m. Okay, so that exponent now applies to each of those variables inside the parentheses. And the same thing is true, right? So they started out multiplied, so we continue to multiply. Same thing would be true if we have a fraction inside this parentheses. This fraction, remember, means a division. This is a divided by b. If we were going to raise that whole term to the m power, well, that a is going to get raised to the m power, and so is that b. But we're going to preserve that relationship between the two of them. That operation that was there to begin with, we're going to keep it. That's that division bar. So this becomes a to the m over b to the m. All right, so let's consider a few examples here. So for example A, this is 5 to the third power raised to the second power. So we're going to go ahead and we're just going to multiply those exponents. And that's going to give us 5 raised to the 6th power. And we don't have to, for the purpose of this example, simplify further than that right now. Okay, now we've got multiple terms raised to the exponent. And each of these terms already has its exponent inside. So we're going to take that 3 to the 4th, raise it to the third power, so we have to multiply that 4 and that 3. And then we've got that x squared. Now it's also being raised to the third power, so we have to multiply that 2 times that 3. And this 3 to the 4th and this x squared, these are also just being multiplied, so we can just write them next to each other. We can write a little dot in between them to denote that they're being multiplied, but we're going to preserve that relationship that they started with. So we've got 3 raised to the 12th power here, x raised to the 6th power. And these are multiplied. That's how that simplifies out. Now we've got a fraction. And in each case, so the numerator already has its exponent, the denominator already has an exponent. So each of these terms is getting raised to this third power further. So we've got 2 to the 5th raised to the third power, so we're going to have to multiply that 5 and the 3. On the bottom, we've got b to the 4th raised to the third power, so we're going to multiply that 4 and that 3. And this is going to give us 2 to the 15th over b to the 12th. All right. Now there's a lot going on in this next one. So we've got multiple terms in both the numerator and the denominator. Every single one of these terms is getting raised to the 5th power. Okay, so let's see how that looks. So first of all, we've got -2 raised to the 5th power. And that negative is going to go in there with that 2. It's not a separate -1 that's being multiplied. It's a -2 times -2 times -2 times -2, so on, right? Every single time. And then we've got m to the 6th raised to the 5th power. I'm just going to write it like this for a second so we can kind of visualize what's going on first. On the bottom, we've got t squared raised to the 5th. And we've got, well, this is just a z to the 1st power being raised to the 5th power. we can just go ahead and write that right away as z to the 5th. It's just really just z being raised to the 5th power. Okay, so negative 2 raised to the 5th power, that's going to come out as negative 32. We've got, right, you can do that operation on the side if you like, negative 2 times itself. But whenever you have a negative value raised to an odd power, it's going to stay negative. Okay, negative values raised to an even power, they're going to become positive. That's just a quick rule of thumb. All right, then we've got m to the 6 times 5. Remember, we have to multiply these, so that becomes m to the 30th power. Down here, we're going to do the same thing. 2 times 5, that's going to become t to the 10th power. And the z to the 5 remains as it was. So this is going to be our final answer here. Okay, we'll just box off all of these final answers. Okay. Next, let's just consider what happens when we have 0 as an exponent. So in general, a, where a is not 0, a non-zero value, a raised to 0 power is going to be equal to 1. That's how it's been defined. Okay, the reason for this is, suppose you had a to the n power times a to the 0 power. Well, according to our product rule, right, we have to add these powers. So this would be, when there's a product of this, the base is the same, we're just going to do the addition here, n plus 0. So that would just come out to anything plus 0 is just itself, so it just comes out to a to the n power. So multiplying by a to 0 here didn't actually change anything. So it's no different than if we just had multiplied by 1. Right? So if we just multiplied a to the n times 1, we would have just been left with a to the n. That's the situation here. Okay. Now let's look at these two examples real quick. We've got negative 4 in parentheses raised to the 0 power. It's going to follow that rule. A here is not equal to 0, so we can apply this rule. This is just going to come out to 1. The base in this case is negative 4. Now, in our second case, we don't have the parentheses here. That negative is not being raised to 0 power. Okay, only the 4 is being raised to 0 power. And by PEMDAS, we're going to do that exponent first, and then we're going to do this multiplication by negative 1 at the end. So you want to think about this as negative 1 times 4 raised to 0 power. Negative 1, in other words, times 1, and then the answer is going to come out to negative 1. So in this case, the base was just 4, not negative 4. Okay, so that's just an important distinction to keep an eye out for, so you don't get your signs mixed up. All right. Next, let's talk about negative exponents. So what if we have something like a raised to the negative n power? Well, what this really means is this is the same thing as 1 over a to the n power. And this actually works the other way too. So if we had a negative power in the denominator of a fraction, this is the same thing as bring it to the other side and just making it positive. Bring it to the other side of the division bar, making that exponent positive. That's really all we're doing. Okay? So it's kind of an indication that you need to flip this to the other side of that division bar. Okay? So let's look at some examples real quick. If we got 4 to the negative 2 power, we should be thinking of this as 1 over 4 to the second power, or 1 over 16. Now we've got negative 4 to the negative 2, but that negative is not inside the parentheses, so it is not going to be raised to that exponent. So what we should be thinking of this as is negative 4 raised, positive 4 by itself raised to the negative 2 power. So that negative comes out here. We can put that 4 on the other side of the division bar and make the exponent positive. This is going to become negative 1 over 16. Okay, Well, now we've got a fraction inside of here raised to a negative power. Okay, well, the logic still applies. If we're looking at it this way, right, we're just putting it under 1. So let's put that whole thing under 1 and make that 3 a positive 3. Now, if you remember, right, if we're raising something like 2 over 5 to the third power, we're going to raise the top to the third power, we're going to raise 125. So now this is going to look a little messy. Bear with me for a second. So we got 1 over 8 over a 125. So that 8 over 125 is your entire denominator on this big kind of overarching fraction. When you have a fraction like this under 1, all it means is take the reciprocal of it. It just means we can flip this thing and make it 125 over 8. All right. A different way you could have thought about this, when you see something like 2 to the 5th raised to the negative third power, you can kind of just think of this as 5 over 2 raised to the third power. Right, now once you understand the rule, you can kind of just do the shortcut method in your head. And then you're raising each of these to the third power, so you're going to get 125 over 8 anyway. Okay. Then we've got x times y in parentheses, both of them raised to the negative third power. That is going to go underneath 1. Make that exponent positive. And now individually raise the 3, or the x to the 3 and the y to the 3. So 1 over x to the third, y to the third. Okay, now here it's important to see there's no parentheses. This x is not being raised to the negative third power. It's only y. So you should be thinking about it like this. It's x times y to the negative third power, which means it's x times 1 over y to the third power. In other words, x over y to the third power. Okay? Let me just box over the answers. All right, so that's negative exponents. This is telling us that we need to take whatever we have and put it underneath 1. And then make that exponent positive. Okay, then we've got quotient rule for exponents. So what happens if we have, this is kind of like the opposite of product rule, what we started with. Originally we started with something like a to the m times a to the n, and then we turned that into a to the m plus n. Well, this is the opposite sort of case here. So we've got a to the m divided by a to the n. And what we're going to do is we're going to turn that into a subtraction. So it's a to the m minus n power. Okay, so an important note here is make sure that you're subtracting the exponents in the correct order, right? So we're given m on top, n on the bottom. It has to be m minus n, not n minus m. Okay, so it's whatever's here in the numerator minus whatever's here in the denominator. Not the opposite way around. That'll give us something different. Okay, so if we're looking at this, well, we've got the 5th power in the numerator. We've got the 2nd power in the denominator. So we're going to do 12 to the 5 minus 2. This gives us 12 to the 3rd power. Here, in example B, we've got a to the 5th in the numerator minus whatever's in the denominator. Now what's in the denominator is also a negative power, right? So we're going to make sure we put in parentheses. So when we're subtracting a negative, we have to make sure that becomes a positive, right? So it's the same thing as 5 plus 8, or a to the 13th power. Now, part C. We've got some numbers here that don't have anything to do with the powers, so let's just separate them. Let's write them out here. And then we've got m to the negative 9 on top, m to the 11th on the bottom. So we're going to subtract negative 9 minus 11. And if we simplify this fraction, this is going to come out to 4 over 3. I can divide top and bottom by 3. And then Well, m to the negative 9th minus 11 is going to give us m to the negative 20. Okay, you can leave it like this, or actually we don't want to leave it like this, we want to take care of that negative, right? So we can put that in the bottom, so we can do m to the 20, put it in the bottom and make it positive. So 4 over 3 m to the 20. All right, then we've got in part D finally, 25r to the 7 z to the 5th over 10r to the 9th, and just z to the first power. So I would just think of this as 5 times 5. We've got r to the 7, z to the 5th. Then on the bottom, we've got 5 times 2, r to the 9th, and z by itself. And we can go ahead and cross out those 5s to simplify this. So we've got 5 halves. Then let's think about our r terms, right? So we're considering it with the same bases. So first these r's together. Well, we've got 7 on the top, 9 on the bottom. This is going to become r to 7 minus 9. Now let's consider the z's. So we've got 5 on the top, 1 on the bottom. So this becomes z to the 5 minus 1 power. Okay, so we've got 5 halves, r to the negative 2, z to the 4th power. Okay, now we're not 100% done yet. Remember, we have a negative power. That's going to come into our denominator. So 5z to the 4th is in our numerator, 2r to the 2nd power. So that r is going to go into the denominator, and we're going to make that exponent positive. And this is going to be our final answer here. All right, now let's consider the last section of R4, last topic of R4, which is rational exponents. So this is when you have an exponent that is itself a fraction, like 1 over n. So if you have something like a to the 1 over n power, what this translates to is actually the nth root of a. All right, so we may be familiar with something like the square root, say, of 4. This is the same thing as 4 raised to the 1/2 power by this definition. Okay, so this is, in other words, this is the inverse of raising something to the 2nd power, right? These operations, the square root and raising it to the 2nd power, they cancel out and you get back your original value. And the reason for that is actually going back to the power rule, right? So if we were to have a raised to the 1 over n and then raised again all of that to the n, we have to multiply these exponents, which is going to give us n over n, which is just 1. So we just get back whatever our original base was in the end. Now there's a couple of rules that apply with this. So when n is even, so it's an even power, right, in that fraction, and a is a positive value, then it means that a to the 1 over n is the nth root of a, just like we said here, right? So this is 4 raised to the 1/2 power is just the square root of 4, right? If you had 4 raised to the, say, 1/4 power, then this would be the 4th root of 4, right? Okay. Right, so this is important. So n has to be even, a has to be positive. Now, if we had a negative number inside of that for a, this wouldn't work because the even root of a negative number is not a real number. Okay, so let's look at these two examples real quick. Again, the same one, 4 raised to the 1/2 power. This is the same thing as the square root of 4, which comes out to 2. If that were instead of negative 4, then this means we're trying to take the square root of a negative number, which is not a real number because there's no number we can multiply by itself to get a negative 4. Okay. On the other hand, when n is odd, a can be any non-zero real number. And now this is going to work. So it can be positive or negative. Okay, so a to the 1 over n is the positive or negative nth root of a. So what does that look like? You could have something like 27 raised to the 1/3 power. This is the same thing as saying the 3rd root or the cube root of 27, which is 3. The reason being 3 times 3 times 3 is 27. But this also works now because this is odd. The nice part is, right, we're multiplying 3 numbers. So we can actually obtain a negative. Let's see how that works. So if we had negative 27 as our base, and we tried taking the 1 raised to the 1/3 power, which is the same thing as taking the cube root of it, this is going to come out to negative 3, because negative 3 times negative 3 times negative 3 is in fact negative 27. Okay, so you can obtain a negative number when you've got the same number multiplied by itself an odd number of times. So 3 times, or 5 times, or 7 times, and so on and so forth. But you can't do that when you have, say, just negative 3 times negative 3. This is going to give you a positive number. So there's no way to get a negative out of an even number of operations here. Okay, so that's why when n is odd, we can do this for positive or negative. But when n is even, then a has to be positive. There's no way to get a positive number. There's no way to get a negative number with an even number of multiplications, but you can get a positive number that way. All right, so let's look at some examples here. 36 raised to the 1/2 power. So this is the same thing as saying, the square root of 36. Okay, which is just going to be 6. 6 times 6 is going to give us 36. Now let's suppose you had negative 100 raised to the 1/2 power. So that negative is going to come out as a negative 1 up front. It's not within the parentheses. It's not being raised to that 1/2 power. So we've got negative 1 times 100 to the 1/2 power. Well, 100 to the 1/2 power is really just the square root of 100. Just a different way of saying the same thing. Square root of 100 is 10. We're going to be left with negative 10. Same idea here. Now we've got parentheses that help us kind of visualize this difference. It says negative is outside the parentheses, and it's staying there. 225 raised to the 1/2 power. That's the square root of 225, which is just 15. So this entire thing comes out to negative 15. Next, we've got negative 1,296 raised to the 1/4 power. So this is the same thing as taking the 4th root, right? That negative is now inside of here. It's being raised to that 1/4 power. This is the 4th root of 1296. We're trying to take an even root of a negative number. That's not going to work because there's no number that we can multiply by itself 4 times that will give us a negative number, right? We can only obtain a negative number if it's negative something times positive something, right? Or positive something times negative something. That's the only way it can work, right? So there's no way these numbers can be the same. So this does not have a real solution. There's no real number that will answer this question. Okay. And finally, we have negative 32 raised to the 1/5 power. Separate that negative 1. All right, it's 32 raised to the 1/5 power. This is the 5th root of 32. The question you're asking yourself is, what number can I multiply by itself 5 times to get 32? And you may or may not know this. This is why it's helpful to memorize, the powers of 2 and powers of 3. But 2 multiplied by itself 5 times is 32. Okay, so we get negative 2 in the end. All right. This can get a little bit more complicated, of course. In math, it can always get a little bit more complicated. You might have something like a to the m over n power. Now, there's 2 different ways of thinking about this. You can think of this as, well, this is just a to the m, all of it raised to the 1 over n power. And that's why we multiply them together and put them like this. Or I can think of it as I'm doing the 1 over n, the nth root operation first, and then raising everything to the m power. Okay, so there's two separate exponent operations that are happening here. And it's going to be helpful to kind of write them out, separate them out. And let's see which order might actually be more useful for us in each case. So I have raised to the second power, and then this is really just the 1/3 operation, right? So I could have written this as, say, 1/3 here, and then raise that whole thing to the second power if I'm using this definition, or this way of looking about it. Well, raising something to the 1/3 power is really just the same thing as taking the cube root of it. Okay, and the cube root of 125, which number multiplied by itself gives you 125? That's just 5, right? So 5 times 5 is 25, times 5 is going to give you 125. So this entire thing is really just going to be 5. Inside the parentheses, 5 squared is 25. Okay. So it's easier to think about the cube root of 125 first, rather than squaring 125 first and then taking the cube root of that giant number. That would work too, but that's a lot more difficult. So why do you want to make your life more difficult? Keep it simple. Same idea here. Instead of doing 32 to the 7th power, why don't we take the 5th root of 32 first, and then raise that to the 7th power? Right? That's just 2. 2 raised to the 7th power is a lot easier to do than 32 raised to the 7th power. And this comes out to 128. Okay? We've got a negative. That negative is not in the parentheses. We're going to bring that out front, and we're not going to apply the exponent to it. Okay, so now we've got 81 raised to 3/2. Let's do the same thing. Let's take that square root first. Right? You can think of this as 81 to the 1/2 first, and then raise to the 3rd power. So 81 to the 1/2, square root of 81, same thing. It's just 9. And you've got -1 times 9 raised to the 3rd power. 9 raised to the 3rd power happens to be 729. -1 times 729 is -729. All right, and then the last one, well, we've got -4 raised to 5/2. Let's try the same idea. Let's do the root first if we can. Right, so you can think of this as -4 raised to the 1/2 power, all of it raised to the 5th, which is the same thing as the square root of -4, all of it raised to the 5th, but we can't take an even root, like a square root of a negative number. That's going to lead to something that is not a real number. All right. So that's that. Now we've got a little bit more complicated examples here. Let's see how these work. This is putting together a little bit more of our rules with fractional exponents or rational exponents. Well, we've got 27 to the 1/3 times 27 to the 5/3, all of it divided by 27 to the 3rd power. Well, let's not forget, we started our discussion of exponents with the power rule, right? Which was a to the m plus n. So let's start with that. This would give us 27 to the 1/3 plus 5/3. And these have the same denominator. That works out nicely. That means we can just add these fractions as they are. And that's going to give us 27 to the 6/3. All of that over 27 to the 3rd power. 6/3, well, I can just simplify that. That becomes 2. Okay, well, I've got 27 to the 2nd power divided by 27 to the 3rd power. This is going to come out to that quotient rule, right? A to the m over a to the n is equal to a to the m minus n. So let's go ahead and do 27 to the 2 minus 3. That's 27 to the -1, which is the same thing as 1 over 27. All right. Another way you could have looked at this is you could have come from here, this 27 to the second over 27 to the third. 27 to the second is just 27 times 27. On the bottom, you have 27 multiplied by itself. And if you really wanted to, well, you can just cross these out, right? These just become ones. So you would see you're also just left with 1 over 27 in that case. Either way works. Okay. These are going to be a little bit more complicated. Let's make some room here. So we've got 81 to the 5 over 4 and 4 to the negative 3 over 2. Well, let's think about this first one as the fourth root of 81. That's what that 1 over 4 is, right? All of it raised to the fifth power. And then how about the square root of 4? All of it raised to the negative third power. We'll deal with that negative in a second afterwards. So let's just simplify what we're dealing with first. So the fourth root of 81, that's what number multiplied by itself 4 times is going to give us 81? That's going to come out to 3. So this first term just simplifies to 3 to the fifth. The square root of 4 is just 2. This is going to come out to 2 to the negative third. Okay. 3 to the fifth, if we multiply that by itself 5 times, that's going to come out to 243. Okay. Then we've got this 2 to the negative third power, which is really just 1 over 2 cubed, or 1 over 2 to the third power. So we've got 243 times 1 over 8. As you know already, a whole number is really just, if we wanted to write that as a fraction, it's just itself over 1. We can multiply straight across. We're going to get 243 over 8. And finally, our last example. There's a lot going on here. So we've got rational exponents. We've got fractions in both these parentheses. And we've got all of that expression multiplied by a similar term or similar expression. Okay. Let's start by just raising everything in here to this power, right, in both cases. So we've got a squared out there, and we've got a 2/3 out there. Okay, so this 3 is going to get raised to second power. This m to the 5/6 is going to get raised to second power. Y to the 3/4 is going to get raised to second power. So how's that look? So we've got 3 squared, m to the 5/6 times 2, 5/6 times 2, that's going to come out to 5 over 3. Then you've got y to the 3/4 raised to second power, so it's going to be 3/4 times 2, so that's going to become y to the 3/2. Okay, so that's our first set of parentheses. Our second one, we're going to do the same idea. Everything is going to raise to this 2/3 power. So we've got 8 to the 2/3. We've got y to the third times 2/3. So 3's are going to cancel, right? So it's just going to be y squared that we're left with. And then we've got m to the 6 times 2/3. 6 divided by 3 is 2. 2 times 2 is going to be 4. So we've got m to the 4th here. Okay. What's next? Well, 3 squared is going to be 9. We've got m to the 5/3. And all of that's divided by y to the 3/2. Then I've got 8 to the 2/3, which 8 cube root of 8 is 2. 2 squared is 4. And then I've got y squared, and I've got this m to the 4th here. Now let's just think about combining like terms. So if we put all of these together, the 9 and 4 are going to come together as 36. We can deal with the m's together, so we've got m to the 5 over 3 over m to the 4th. We can deal with the y's together, so we've got y squared over y to the 3/2. Okay, so this is going to be m to the 5/3 minus 4, y to the 2 minus 3/2. All right, so we've got a fraction subtracting a whole number, and here we've got a whole number subtracting a fraction. So our only goal here, the only thing we have to worry about is let's just make sure they have the same denominator. So 4 written as a number with a denominator of 3, that's going to be 12 over 3. And 2 written as a number with a denominator of 2 is going to be 4 over 2. Right, so you can think of these as ones. We're going to do the same operation on the top and bottom. This can give us those values. Okay. 5/3 minus 12/3, that's going to give us negative 7/3. 4/2 minus 3/2 is going to give us positive 1/2. Let's not forget, we have a negative exponent. That's going into the denominator, and we're making it positive. And that is going to be our final answer. Okay, and that's about it for R4, exponent rules.